Statistical process control. In this unit, we will cover statistical process control. We will review the variation found in a typical process. We will discuss the methods used for taking samples and the types of data reviewed. We will analyze the typical distributions of data and use this knowledge to create control charts. The goal is to reduce variation in a given process. Statistical process control applies statistical analysis to the assignable causes of variation to identify when corrective action should be taken. Process variability has two causes, random and assignable. The goal of SPC is to reduce or eliminate assignable causes of variation. Some variability is inevitable. The goal is to ensure that product variability falls within acceptable limits. Some practitioners believe that the variability deemed to be random is simply assignable variation that is yet to be fully understood. To manage and control a process, we need to measure it. Samples of product produced on the production line are taken and measured. The measurement results are used to analyze the process. In this example, boxes of cereal are pulled and weighed. Each sample includes 5 boxes. The results are plotted on a graph showing the frequency of each weight. We find that if we gather data from enough samples, we will generate a distribution curve as shown here. When taking sample data, there are many possible distributions. 3 different types of distributions are shown here. They include a shift in the mean, a shift in standard deviation, and a shift in shape. If the process is stable over time, the sample distribution will not vary and is predictable. In this case, assignable causes are present, and the distribution is not predictable over time. Control charts use a statistical analysis of past data to distinguish between natural variation and variation due to assignable causes. There are 2 main types of data in a process. Attribute data is qualitative. There is a discrete choice, good, bad, acceptable, unacceptable. Variable data is quantitative and can be measured on a continuous scale. Think of length, size, weight, temperature, time, and velocity. The central limit theorem describes the relationship between sample data and the true distribution of the process. The distribution of sample means will follow a normal curve. The mean of the sampling distribution will match the population mean. Finally, the standard deviation of the sampling distribution will equal the population standard deviation divided by the square root of the sample size. We will provide detail on P-charts for attribute data, along with X-bar and R-charts for variable data. This chart is here to give you an idea of how these charts relate to sample distributions. In this example, the standard deviation is not changing, but the mean is moving up. Note the movement in the X-bar chart as the mean changes over time. But since there is no change to the range, the R-chart is constant. This is the opposite situation where the mean is unchanged, but there is increasing variance. The X-bar chart is constant, but we see the R-chart value increasing over time. When a process is in control, there should be no data points outside of the upper and lower control limits. Most points should be found near the mean, with the same number of points above and below the line. Finally, there should not be a trend upward or downward. A trend suggests that the process will be out of control over time. Consider these examples of control charts. The chart in the upper left portrays a process that is in control. The process shown in the upper right should be checked since one point is out of control. Plus, the other points tend to be above the mean. The chart in the lower left shows a process that is under control, but has a trend suggesting that the process will be out of control soon. Proactive steps are needed to reverse this trend. Finally, the process chart in the lower right corner is under control, but should be checked because the points vary wildly. This suggests a process likely to go out of control. In summary, 3 of the 4 processes are under control graphically, but 2 of these require further investigation. Now that we understand the use of control charts, we will explain how the control limits are set. For X-bar charts, the upper and lower control limits are calculated by the mean of the sample means plus and minus the product of the number of standard deviations z and the standard deviation of the sample means. In this example, we have taken hourly samples from production over 12 hours. Each sample has 9 boxes in it. The resulting measurement averages are shown here. For example, the first sample of 9 boxes had an average weight of 16.1 ounces. This average is simply the sum of the 9 measurements divided by 9. The next step is to calculate the mean of the sample means. This is simply the sum of the averages divided by the number of samples. This would be 12. This is often confusing for students. We must remember that n, the number of items in each sample, is 9, while the number of samples, how many times we take samples, is 12. To calculate, we sum the averages 16.1 plus 16.8 plus 15.5 plus 16.5 plus 16.5 plus 16.4 plus 15.2 plus 16.4 plus 16.3 plus 14.8 plus 14.2 plus 17.3. The total is 192. Dividing 192 by 12, we get that X bar equals 16. Given the data, we substitute the values into the equation for the control limits. The upper control limit is 17 ounces, while the lower control limit is 15 ounces. Here is a graphical depiction of a control chart based on our previous calculations. We see the mean at 16 ounces with the upper and lower control limits at 17 and 15 ounces respectively. We have since plotted some mean data over time. Note that each data point represents the average of the weights of 9 boxes from a single sample. We see that 3 sample means are out of range, indicating a process problem that may be due to assignable causes, not random variation. In the previous example, we knew the standard deviation. We now consider data when the standard deviation is unknown. In this case, the upper and lower control limits are defined as the X bar mean of sample means plus or minus A2 multiplied by the average range of the samples. A2 is a control chart factor found in many texts. It may also be found on the internet. Here is a table of standard A2, D4, and D3 values from the table. The D3 and D4 values will be used later. Note that the values vary as a function of the sample size. The sample size is the number of items tested in each sample. If I walk out to the factory floor and pull 10 products and measure them, the sample size n equals 10. Here we have collected data on some cola bottle inspection results. Each time 5 bottles are weighed, so the sample size n equals 5. Samples were taken 10 times. The second column shows the weight of the lightest bottle, while the third column shows the weight of the heaviest bottle in each sample. The final column shows the range, which is the difference between the second and third columns. We take the average of this last column to get an R bar of 0.25. We are given a mean of means X bar of 12 ounces. With a sample size of 5 bottles, we have an A2 value of 0.577 from the table. Substituting the values into the equation, we get an upper control limit of 12.144 ounces and a lower control limit of 11.856 ounces. We now have everything we need to set up our X bar control chart, started on the right. Now we turn to the R chart. This is another variable control chart. This chart does not show the mean, but shows the variation of sample means over time. This chart is independent of the process mean. Setting the upper and lower control limits for R charts uses simple equations. The upper control limit is the D4 value from the table multiplied by the average range R bar. The lower control limit calculation is the same except using the D3 value from the table. Here's an example X bar chart and R chart showing the mean and range of weight measurements for salmon fillets at Darden restaurants. There appears to be one sample, number 11, that should be investigated, but otherwise the process appears to be well under control. This example measures response time with 4 observations with each sample, n equals 4. Samples are taken on 5 different occasions, k equals 5. We see the 4 observation values for each sample. We identify the lowest and highest values, and the difference is the range. Taking the average of the range values, we get an R bar value of 8 minutes. We plug the R bar value from the previous calculation and the table values for the D4 and D3 statistics into the equations. The result is an upper control limit of 18.256 minutes and a lower control limit of 0 minutes. The start of the R chart is shown at the right. This slide shows the general steps to create control charts. We start with multiple samples of 4 or 5 observations each. Next, the X bar and R bar values are calculated from the sample data. These values are used to calculate the upper and lower control limits. These steps assume that the process is stable. If not, use the desired mean instead of the measured mean values to set the control limits. Next, we create the control charts from the previous data. Using the control charts, plot the actual measurements over time. Action plans would be created to resolve any issues identified by the process limits. Once complete, process data is gathered and plotted to confirm the impact of the improvement. The process limits may then be readjusted if appropriate. Instead of using measurement data to identify limits, confidence levels might be used. The control limits are based on the z-value or the number of standard deviations considered. For example, 90% confidence requires a z-value of 1.65. The values may be found in a standard z-value table from many texts or from the internet. We will cover p-charts, which are used for attribute data. Remember that attributes are discrete, such as good or bad. Counting defective product is a common use of p-charts. Here we see the equations for the control limits for p-charts. We can assume a normal distribution where the upper and lower control limits are the mean fraction of defective units, p bar plus n minus the z-value multiplied by the standard deviation of the samples, sigma sub p. Sigma sub p is estimated by the square root of p bar times 1 minus p bar divided by n. N is the number of observations in each sample. For this example, we see that 20 samples were taken with 100 records checked in each sample. The number of errors is shown along with the fraction defective. The fraction defective is the number of errors divided by 100. The number of records checked. We see that the total number of errors from the 20 samples was 80. Using this data, we start by calculating p bar using the total number of errors, 80, divided by the number of records checked, which is 20 samples times 100 records each. We find that p bar equals 0.04. Substituting the value of p bar and n into the standard deviation equation, we get a value of roughly 0.02. Plugging the p bar, sigma, and z values into the equations, we obtain an upper control limit of 0.10 and a lower control limit of 0, since we can't have a negative % defective. Since we are using a z-value of 3, We are looking for 99.73% confidence in our process outcome. This P-chart shows the results of our inspection records. The mean P-bar and the upper and lower control limits are shown. Looks like there is an issue with sample number 17. We have discussed assignable variability within a process that may be corrected through analysis and process improvement. What's left is the natural variation of the process. This would be considered a process that is under control. The problem is that the design specification to meet customer needs may be different than the capability of the process. To assess whether a process meets customer specifications, we calculate the process capability ratio. CP is the difference between the upper specification and the lower specification divided by 6 times the standard deviation of the process. We are comparing the process variation with the allowable specification tolerances. This is an analysis of variation and does not address the mean of the process. Six Sigma requires a CP of 2.0, while a target of 1.33 is often used to allow for process variation. The goal of the process capability index, CPK, is to be greater than or equal to 1. A CPK greater than 1 suggests that the process will create product that, while not centered, will fall within the customer specification. This slide shows the result of a process having different values for CPK. The fourth example, where CPK equals 1, is the minimal target for the process to be within specification. Obviously, a CPK greater than 1 is ideal and allows for more process variation while staying within specification. Key points to remember. Variation exists in any process. Variation may be due to natural variation or assignable causes. To assess a process, we take data. Given enough samples, this data will approach a normal distribution. We use this data to understand the mean and variation of the process. These measures are used to create control charts. The data may be qualitative or quantitative. Qualitative or attribute data is on-off and is tracked on a P-chart. Quantitative or variable data is a characteristic on a continuous scale, like size or temperature, and is tracked on X-bar and R charts. These various control charts track mean and variance. We look for data points outside of defined control limits. These control limits are calculated in different ways for each control chart type and based upon the confidence or service level required. The process, while under control, may not match customer specifications. CP and CPK measure the alignment between the process capability and the customer specification. You want a CPK greater than or equal to 1.